Hey everyone, and welcome to this explainer. This one's brought to you by Forge College. Now, if you hung out with us for our last lesson, the Capstone Final Deploy and Reference Guide, you are absolutely primed and ready for what we're tackling today. We are officially crossing the bridge from the EVM, the Ethereum Virtual Machine, over to the SVM, the Solana Virtual Machine. And look, I'm going to be real with you. This is a massive paradigm shift. It requires completely, and I mean completely, rewiring your mental model of how a blockchain actually stores and interacts with data. But hey, don't sweat it. We're going to build this new mental model together from the ground up, starting with the absolute bedrock of the Solana ecosystem, the core principles of Solana accounts.
Okay, let's dive into this. This is the fundamental difference that trips up, honestly, almost every single EVM developer when they first arrive on Solana. So in the EVM model, a smart contract is kind of like a house, right? And it has a safe built right into the living room wall. The code and the state, the actual data it holds, are bundled together under one single address. But in the SVM model, executable programs and data accounts are completely separate. It's way more like a bank. The bank teller, that's your program, has the instructions on how to process the transactions. But the actual money, the data, well, that's kept in completely separate safety deposit boxes, which are the accounts. The programs themselves are essentially stateless. So if you want a program to update some data, you've got to explicitly pass that specific data account to the program during the transaction. It's a total separation of code and data, and it changes absolutely everything about how you build. To help make sense of this new architecture, we've got a clear, four-part blueprint for you today. First, we'll look at the anatomy of an account. Second, we'll explore the cloud hosting metaphor. Third, we'll map out the transaction lifecycle. And finally, we'll wrap up with the golden rules of design.
Let's jump right into Section 1, Anatomy of an Account, looking under the hood.
Now, what's really interesting about this is that to truly master the SVM, we need to pop the hood and identify the 5 core components of its primary building block. Literally every single piece of state on Solana lives inside one of these accounts, and these 5 simple fields dictate the entire reality of the network. First up, you have lamports. And this isn't just spending money, it's the native sol balance that literally pays for the account's very existence. Next is the owner. This is a public key acting as a strict authority boundary. It designates exactly which program is actually allowed to modify the data. Then, inside the data field itself is just a raw, uninterpreted binary buffer. There is absolutely no built-in schema here. Your program has to know exactly how to read and write those specific bytes. We also have an executable flag, which is just a simple boolean telling the network whether this account holds passive data or active, immutable program code. And rounding the whole thing out is the rent-epoch. Think of this as the network's bookkeeping mechanism to make sure you've actually paid for your storage space.
Moving right along to Section 2, the cloud hosting metaphor, a durable mental model. So think of a Solana account exactly like a file on a shared cloud hosting service, something like AWS or Google Cloud. That lamports balance we just talked about, yeah, that's your prepaid hosting fee. On Solana, validators are storing your data, and let's be real, they certainly don't work for free. You have to maintain a minimum balance to be what's called rent-exempt. It is literally like prepaying for your cloud storage, so your super important files aren't abruptly deleted or evicted just because you forgot to pay your digital utility bill. If you underfund the account, no joke, the network will simply reclaim the space. Now, within this system, the access control list has exactly one principle, and that's the owner program public key. I want you to think of this owner program as the most uncompromising, intimidating bouncer at an exclusive VIP club. This bouncer checks the list, and there is strictly only one name on it. If literally any other program tries to mutate that account's data buffer, the runtime immediately rejects it. No exceptions, no arguing with the bouncer. It enforces a super strict capability boundary that is exactly what makes the network so highly secure. Finishing up our cloud metaphor here, if that executable flag is set to true, it means our cloud file contains a script, immutable code that the network can actually run. If it's false, the file is just a passive data buffer. But, and here is the absolutely critical catch for developers coming over from Ethereum, this data buffer is a pre-allocated disk quota. Unlike the EVM, where you might just assume you can keep pushing items to a storage array infinitely forever, on Solana, you cannot assume infinite storage. If you need a larger file, you have to explicitly resize it, and you've got to pay the extra lamports to fund that new allocation. You get exactly what you pay for.
Okay, let's shift gears to Section 3, the transaction lifecycle, the assembly line.
Let's move to this and see how it all builds together. Solana performs incredibly strict validation before your programs even get to run. It all starts with constructing the transaction, where you have to explicitly declare every single account you plan to use. Then comes signing to prove your intent. That's followed by a pre-flight check, where the network makes sure you've actually paid your rent and that your account sizes are valid. Next up is mapping. This is where the runtime pulls your declared accounts into memory and checks in with that bouncer we talked about earlier, verifying ownership and write privileges. Only after all of that do we finally get to execution, the actual running of your program logic. And then, finally, finalization, where your state changes are persisted to the chain. The huge takeaway here, the runtime only makes the accounts you explicitly declared accessible. If you forget to list one or forget to mark it as writable, boom, your transaction fails instantly.
And speaking of failing, what exactly happens when things go wrong during execution? Well, that's where rollback semantics come into play. If an instruction errors out or panics during execution, the runtime simply reverts all state changes made during that instruction. It acts like a magical undo button, preserving complete atomicity. And honestly, this is fantastic news. It means that partial failures in those multi-step, complex flows are safely rolled back. You don't ever have to worry about a transaction failing halfway through and leaving your precious data in some corrupted, half-updated state.
All right, let's bring it all together in Section 4, Golden Rules of Design, the Blueprint Takeaways.
So the crucial point here is summarizing these 3 golden rules for you to build by. First, ownership is an operational gate enforced by the runtime. You can't just hack your way into modifying data. You absolutely must respect the owner public key. Second, data is pre-allocated and paid for. You always need to plan your account sizing and budget for that rent exemption right up front. And third, transaction-level declaration is literally part of your API. The accounts that you require our user to pass in are just as much a part of your program's interface as the functions themselves. If you follow these rules, you'll naturally start partitioning your state logically, rather than trying to build those massive monolithic EVM-style contracts that quite frankly just don't fit the SVM paradigm at all.
So, to wrap things up, I want to leave you with this question. How will these strict rules of ownership and rent change the way you personally design account abstraction and vaults moving forward? I want you to really think about how this separation of code and data changes where you store user funds and exactly who has the authority to actually move them. Keep that question right at the front of your mind as you prepare for our upcoming lessons in this module. I want to say a huge thank you for hanging out with me on this explainer created by Forge College. If you want to dive deeper into these concepts, master advanced ERC patterns on Solana, and explore a ton of other amazing Web3 topics, head over to Forge College right now. Catch you in the next one.